a vehicle traveling at a speed of 45 miles per hour. So we have a vehicle here, this one, traveling at 45 miles per hour, is followed by another vehicle traveling at a higher speed, 60 miles per hour. So the guy behind is probably approaching and thinking about passing this guy. Now, the leading vehicle suddenly applies the brakes to avoid hitting an obstacle on the highway at an instant in which the distance from the rear bumper of the leading vehicle to the front bumper of the following vehicle is 200 feet. So at the instant this guy hits the brakes, the distance between the rear bumper of this vehicle and the front bumper of this other vehicle is 200 feet. The maximum constant, so in this problem I'm telling you this is a constant acceleration moment, constant acceleration rate for the leading vehicle is 12 feet per square second. So when this guy hits the brakes, it's going to be decelerating at 12 feet per square second. So A1 for vehicle 1 is minus 12 feet per square second. So if the driver of the following vehicle has a perception reaction time of 1.5 seconds, and let me explain what that means. The guy in the front vehicle applied the brakes, and the vehicle behind, the guy in the vehicle behind sees the braking light, right? And it takes some time to react. So for 1.5 seconds, did nothing, continued traveling at 60 miles per hour. After that 1.5 seconds, he also applies the brakes, right? If the driver of the following vehicle has a perception reaction time of 1.5 seconds and his vehicle can achieve a constant acceleration rate of 15 feet per square second, okay, now the question comes, A, determine whether the two vehicles collide, assuming that the only possible evasive maneuver for the driver of the following vehicle is braking. The reason why I added this makes it a little bit more complicated, but you may think, well, the guy was thinking about passing, but let's see someone else showed up on the opposite lane. So he cannot pass. Perhaps you have some obstacles here on the bridge, on a bridge or something. So the only thing that this guy can do is brake. So the question is, given this scenario, do these two vehicles collide or not? Okay. No forces involved. We know essentially what, at some point in time, this guy brakes. Well, while he was traveling at 45 miles per hour, we know the acceleration rate. We know this guy 1.5 seconds after this guy starts braking, is going to start braking as well with this acceleration rate. Do they collide or not? And depending on your answer here, we have a second question, which says, depending on the results, on the result in A, determine the speed of each vehicle at the instant of collision if you concluded that they collide, or the separation between the rear of the leading vehicle and the front of the following vehicle when both have stopped if you concluded that they did not collide. So you have two options. Either the guy behind hits the guy in front, and the question is at what speed each of them were traveling in that situation, or they both were able to stop, and the question asks what distance both at that instant in time between the two vehicles. It's always nice to be able to graph things, and I think Garrett is very careful because you have to be extremely careful with these problems. Basically, what Garrett said is that he figured out the distance that this first vehicle traveled. Let's say he figured out if he got to this point. And then he looked at the second vehicle and figured out, okay, where does this vehicle stops? If he stops here, then the two vehicles do not collide. If they stop here, if the second vehicle stops there, then they will collide, right? At some point they have to collide. Was that your reasoning, Garrett?
Yeah, that's exactly what I.
Okay, perfect. So that's basically what we're going to be doing. And the way I'm going to show you the first part is basically what he did. But I'm going to show it in a different kind of graph, which makes clearer which vehicle is which. So I'm going to show things in what we call a time. I'm going to have time in the horizontal axis and a space in the vertical axis, or position in the vertical axis. And basically what Garrett did is he said, well, I want to look at the position of the vehicle in front, and I want to look at the, in particular for this problem, the collision will occur between the front of the rear vehicle and the rear of the following vehicle. So I want to look at the trajectory of the front vehicle, of the rear of the front vehicle. I think I said the following, that was erroneous. So I'm going to look at that trajectory. So, and you can say, well, I'm going to start looking at that this instant in time. I'm going to call it 0 arbitrarily, right? So I'm saying at this point in time, which they are separated 200 feet, that's my time 0. I define that arbitrarily, right? So you are free to do that. So this vehicle will be at this instant in time, will start decelerating with a deceleration rate of 12 feet per second, right? Or minus 12 feet, an acceleration of minus 12 feet per square second. So it will be a constant accelerating movement. It will be a parabolic movement like that. Now we're going to look at the following vehicle. Let me draw a straight line. So this guy, the guy behind, for 1.5 seconds, continue traveling at constant speed, and then we'll start braking. So from that point on, so after 1.5 seconds, we'll start braking, also with a deceleration rate, which in a constant decelerating moment, in this case, the deceleration rate will be minus 15 feet per second. So I will have another parabola. I'm assuming that when this guy comes to a complete stop here, when the two curves are horizontal, if this guy is ahead, what that indicates that at some point they collide, right? The trajectories collide. At this point, there would be a collision. That was one of the assumptions. It's an assumption that we're making. What Garrett basically did was to figure out, okay, what's the distance that this guy traveled here? Let me call that delta x1 because it was the position, the travel distance, or the difference in position from the initial, from t naught, t equals 0 to when the vehicle stopped. At this point here, I'm saying this vehicle has completely stopped. So that trajectory from that point on becomes a horizontal line. The vehicle stopped. So that delta x1, and then I have, this was 200 feet, right? That was the separation between the two vehicles. So what Garrett did, well, what he did first was, let me figure out what this distance is. This distance, let me call this delta x2 prime. That's the difference in position for vehicle 2 from time 0 to time 1.5 seconds. During that period of time, this vehicle traveled at constant speed. So this is very easy to figure out, right? So it's just v2 times t with the appropriate unit. You will put everything probably in speed in feet per second and time in seconds. You get then the distance in feet. And when this line now becomes horizontal, let me figure out that distance and let me call that delta x2 prime, which I can figure out from a constant accelerating moment very easily. This delta x1 and delta x2 prime, we're going to see what expression we use. And that's it. So he figured out this distance first, right? And then this distance second, and then he concluded, oh, this is longer than that. So my answer to part A is that the two vehicles collide. And that's a perfect way to approach this problem. So let's put numbers on this. The final position, let me call the position from here to there, x1f. The final position for vehicle 1 when the vehicle stops is the 200 feet, so that we have here, plus the delta x1, right? And the delta x1, I'm not going to write delta x1 to save time. You go back and look at the equations for a constant decelerating movement, you could figure out, oh, what's the time it takes for the vehicle to decelerate, to go from a speed of 45 miles per hour to 0. You can figure that time, and then you put that time into the equation for position as a function of time, and you would get the new position, and then you get the different position will give you the distance traveled. Now, be smart. There's an equation that relates directly the square of the speeds at 2 instants in time and the acceleration and the delta x. So that's the equation I'm going to use because it's a lot faster. So in this case, the final speed is 0. So that's the final speed squared minus the initial speed, which is 45 miles per hour. V1 is 45 miles per hour. And get used to, if you multiply that by 22 and divide by 15, that's the conversion from feet per second to miles per hour. So when you multiply by that number, essentially this cancels, and we have that V1 is equal to 66 feet per second. Okay? So that's my initial speed. So it's final speed minus initial speed, 66. Sorry, I missed the feet per second here. Feet per second square divided by 2 times the acceleration. And the acceleration is minus 12 feet per second. So you are decelerating per square second. And you can see in here, I will have feet squared divided by second squared divided by feet per second squared. So the second squares are going to cancel, and the feet squared with feet, I will end up with feet in the numerator. So I have a distance. It's always nice to put the units so you can check that you indeed get with a distance. So when I made the calculations, this 200 feet plus 181.5 feet or 381.5 feet. Okay, now for the second card, let me check the chat if there's a question there, or could you write the equation you're using for reference? It's in the notes. Let me just point it out. You have it here, right? This delta x equals b squared minus b naught squared divided by 2a. So that's the equation I'm using. So let's look at the second x. Let me call this distance now, the total distance, the final position for vehicle 2, x2f. That's equal to this delta x2 prime. That's v2 times t, and v2, again, making the conversion, v2, it's 60 miles per hour, but in feet per second, that gets to be 88 feet per second. So I'm going to say the time there. So it's 88 feet per second multiplied by the time during which you were traveling at a constant speed, which is 1.5 seconds. So the seconds cancel and we end up with feet there. And to that, I'm going to, again, from this point forward, I have a constant decelerating movement. So again, I'm going to use, and it saves you a lot of headaches in this case to use the same equation that I used before, the final speed squared minus the initial speed squared divided by 2 times the acceleration. So the final speed is again 0 square. I'm going to put just 0 there. Then we have the initial speed is 88 in this case, square. And obviously that would have units of feet squared divided by second square, divided by 2 times the acceleration rate, which is minus 15 feet per second square. And again, you see the square, these second squares cancel, feet cancel with the square, and end up with feet. So if you make all the calculations, all the computations there, you get that this car traveled to stop 390.1 or 0.13 feet. So at this point, you can say that, oh, since x2f is greater than x1f, because of that, the vehicles must collide. So, and this is a nice way to approach the problem, because this way, you know ahead of time, well, they collide or they do not collide. And then that helps you to answer the second part of the question. Well, if they do not collide, once you figure out where the two vehicles stop, you know, at this point, you will know these two distances, you can make the difference and get the separation between vehicles. Or if you conclude, like in this case, if they collide, this a little bit, it could be a little bit more tricky depending on what you do next. And that's why I don't like to give you a recipe. I want you to follow the logic, your own logic, but making sure that you check all your assumptions. So one of the things that I think Garrett did, and correct me if I'm wrong, I think you mentioned that, okay, you figured the total distance, and then you figured out this. What did you figure out next then? Once you knew this distance?
Yeah, so to figure out the velocity of the first car is 0. You can deduce that just from looking at the graph. But then the velocity of the car behind, you have to actually take the slope of the graph at the time of collision, and then that'll give you the velocity.
Well, how did you get the time of collision? That's what I mean.
Oh, the time of collision is from the graph. So it's not where they intersect necessarily, but it's wherever. So if the first car made it 381 feet, then at the time that the second car made it 381 feet, that's the time of collision.
Okay. So notice that you made an assumption there. You assume the other car is already stopped. That's an assumption.
Yeah, the car had stopped, and then like it starts reversing, but obviously it doesn't reverse. So you have to take it from the distance and not where they intersect.
Yeah. What you did is absolutely right, and you got the right answer, because that's the right assumption for this problem. So what I'm saying is that you are making the assumption that the collision is going to occur when this car, the car in the front is stopped, and the other one is going to come from behind and hit it. You are making that assumption. And in your case, it comes out with the right solution, because the data in this problem, that's the right solution. Maybe you realize that, but I'm telling you, and for the rest of the class, right? That's the right assumption in this problem. And it goes back to these graphs that you see here. Many times I like to start the problem like this. I'm making the assumption this vehicle is accelerating, the one behind is also accelerating, but hits it before the vehicle stops. And if I change the data, that could be the case. You see this? The red line is very mild, but still going up, right? So in this graph, I assume that this vehicle is still moving while the vehicle in the back, the one in black, collided with it. So it's possible that both vehicles are moving forward when they collide. So you assume that the vehicle in front had stopped. Did you double check that your assumption was correct?
So actually, you can tell from the graph, you can tell where in the graph that it reaches 381 feet if the vehicle is stopped or not. So it makes a parabola, and it depends on the parabola. Looks like this. If the car hits it on the first half of the parabola.
Let me take a look at you because I don't see you. Okay, can you say again? Yeah.
Oh, okay, sorry. So the parabola of the first vehicle looks like this.
Yeah.
Well, at the top of that parabola is where the vehicle stopped. So the second car, if the parabola reaches 381, like the first half of the parabola, first car is still moving. If it reaches 381 feet on the second half of the parabola, the car had stopped.
Yeah. So did you graph that with Excel?
No, I just used Desmos.
Decimals, okay, it's something to graph, right?
Yeah, it's just a graph.
Okay. So, and that's one of the things one of the reasons why I put so much emphasis, in exams, typically, you would not have been able to do that in a normal exam in this class. Now we have to switch to this, but so you're telling me that you're seeing that, and that's completely true. But when you are trying to solve this on paper, this what not so easy to see. So, but by the way, solving problems like you're doing it is a perfectly valid approach. A lot of things is if you graph them, it's a lot easier to see. And what you're telling me, you knew, hey, this thing was coming down. And I tell you, one of the problems I was having with this, usually with people making the assumption, sometimes people were making this assumption. And the reason why I asked the question, like, what the speed did you find they collide, is because what Garrett is telling me is something perfectly valid, right? So he probably graphed, and that's why I put these two things. For this particular problem, what happens is that the vehicle in front is doing something like this, right? If you plot the function and you don't say, hey, the vehicle is stopping, you're just plotting a quadratic function, it will come back. It's not real because the vehicle now is going to stop and then decelerate, change and start reversing with exactly the same acceleration. That's not real, right? So if you see an obstacle, you see something, you try to stop, and that's it. Then you stop. So beyond that point, that's not real anymore, right? And then the vehicle behind travels at constant speed, and after 1.5 seconds starts accelerating. And what happens in this problem is that if you don't assume what Garrett did, which is saying, oh, after this point I have a straight line, you will find, when you set up the problem where these two lines intersect, you will find that this vehicle was coming back. You would get a negative speed. And you can do this even with Excel. If you don't pay attention, you just draw a quadratic function and then the other one lines intersected. And yes, you're solving a problem that has nothing wrong with the initial assumptions because you don't know. And you get a solution. And I get a lot of times, you don't know how many times I got, oh, the vehicle in front, so the big one, the final speed for vehicle one was equal to -6 or -7 or whatever feet per second, or whatever number that is, a negative number, right? And that should tell you, hey, this doesn't make sense. He's saying that the vehicle stopped because panics. He's not going to start reversing, right? So you have to analyze the problems critically. So there's nothing wrong with starting the problem like I say here, hey, I'm going to set up an equation to find out where these two curves intersect. Nothing wrong with that. That's a perfectly valid thing. But when you find a solution, come back here and check that you didn't find this solution, right? Because for this problem, this is what happened. So when you go and do this and find that, hey, the first vehicle is going backwards, that tells you that something is wrong in your assumption. And then you have to realize, if you plot the problem, if you sketch it, you realize, oh, well, what's happening is that this car is already reversing. That's not real. This is not happening. And then you have to go on and start the problem from scratch, saying, okay, this vehicle stopped at some point, and then this vehicle behind went and hit it at that point. And that's exactly what Garrett did. He assumed, okay, this vehicle had stopped. He had moved 381.5 feet, okay, and then the vehicle behind had stopped. The way to check where that assumption, whether Garrett's assumption was correct or not, now is that you have to make sure that the time to collision, this time over here, when the two vehicles collide, is larger than the time it took for this vehicle to stop. Alternatively, you can use Graphite or whatever the name of the app he used to solve the problem, or Excel, whatever you want to use. But this is where these problems become challenging, because I can give you another set of data where this is what happens. They collide before any vehicle stops. And in that case, this setup will give you the right solution. I like putting things in a time-space diagram, because the time-space diagram, these diagrams over here, these are sketches, right? So, if I'm trying to be careful, I would put here the slope is equal to 0, right? Try to make sure that I make my assumptions explicit. So if we have this, how we solve the problem becomes relatively easy. So we already figured out that distance is 381.5 feet. We're not going to repeat that calculation from before. So let's do this manually. Let's see, this distance doesn't change. We already figured it out too. Let me see, that was 132 feet, okay? So all we have to do is to say, okay, so this vehicle is going to be decelerating here, and this is supposed to be a parabola, right? So remember, I cannot write, I have the screen kind of like there, I cannot produce the curvature there very well, but this is supposed to be a parabola, similar to what I try to do here. So the distance, while I'm decelerating, now I know that distance is the difference between these two things. So I have 249.5. So how do I get that? What am I trying to get first? I'm trying to get the speed of the vehicle behind. If you're just trying to answer the question, that's all we need. So we're trying to get the final speed for vehicle 2. I'm going to subtract from there the initial speed from vehicle 2, which is 88 feet per second squared. The acceleration rate is equal to -15. And I know that because of what I wrote here, that distance needs to be equal. That's the distance over which I'm decelerating to a speed v2f at the time of collision. So I get 259. So from here, if you plug in the numbers, I just did it just to make sure that I'm not giving you the wrong solution. I get that this is equal to 16.09 feet per second. At that point, in most of the problems, the final answer expressed with 3 significant figures. Now, when you get to this point, have you done anything to check that that's true, that this is true? This, to me, very important that you actually check what you do. We haven't checked. Unless you graph it and check that everything looks nice, I don't know that this is truth. So if I want to check that this is true, you see, for this vehicle to be stopped, this time here at which the two vehicles collide has to be greater than this time at which the first vehicle had stopped. That's the assumption we made. So let me call this time to stop and this time to collision. These times. The time to stop is relatively easy. Okay, so the final speed, V1 of the first vehicle, the final speed, I know is equal to 0 feet per second. right? That needs to be equal to the initial speed of vehicle 1, V1 node, plus the acceleration of vehicle 1 times the time to stop, because he started decelerating from time 0 until TS, right? So from there I can figure out the time to stop is basically equal to minus V1 node divided by A1, and that would be minus V1 node was equal to 66 feet per second divided by minus 12 feet per square second. And that will give me 5.5 seconds. Now, how do I get at what time the two vehicles collided? Something very similar to this. I already figured out, oh, the final speed, I know it. If this is correct, I know it. So I could say V2F, which is 16.1 feet, is equal to, notice this equation and the equation that I'm going to write here are valid only for a constant decelerated movement. So I'm going to write an expression that goes from this point to here where the vehicle is decelerating, because I know the speed at this point and I know the speed at that point. So the initial speed is going to be the 88 feet per second, the 60 miles per hour. So this is the initial speed V2 node, plus the acceleration, which is A2, let me write it, it would be minus 15 feet per square second, times, and this is where you have to be careful, times what? You know, in the notes it says the final speed is equal to the initial speed plus the acceleration times t, right? But you have to be careful what t is, because I told you I'm looking at the movement from this point to that point. So I'm looking at that t, in this case becomes the delta t, is the instant in time from this point to that point. So it would be the time to collision minus the 1.5 seconds that I have here, because that's the time during which you are decelerating. The time to collision from that equation is 6.29 seconds. Okay? And now you can tell me, okay, the time to collision, this is greater than the time to stop of the first vehicle, which was 5.5 seconds. So your assumption that the two vehicles collided when the first vehicle had stopped is correct. I want to just write, assumption is correct. Okay? And that's it, end of the problem for you. But like I said, I could have given you, I changed just this distance, I play with this distance, or I play with some speeds, and the problem would look like this. If that were the case, how do you solve this problem? Can anybody tell me how would you set up if making this assumption, and let's assume that this is the correct assumption at this point?
So looking at it, I'm like, well, position and time have to be the same for like everything. So you could use the position, like the equation for position, and then you could like set them equal.
Yes, exactly. So you will have a time to collision, and it would happen at a position that we can call, okay, the X for collision. And you say, well, the X for collision if for this car would be the same as for this car, and the collision would happen at the same time. Okay. And again, it's just a matter of saying it's 200 plus this distance that I don't know, but it would be, I can make it a function of this time. And this one, it will be the same. It will be this distance that it's again 88 feet per second times 1.5, that you know, plus a distance that will depend also on this time. It would be, that distance will depend actually on this time to collision minus the 1.5 seconds. And again, you have to be careful there. But that's exactly the right approach. If you do this, if you do that for this problem, if you start it like this, you will find out actually that the speed of the front vehicle is negative, and that's the way you find out that, hey, my assumption was incorrect. So there are a lot of ways to approach the problem. I'm trying to give you all the alternatives because it's a very simple problem. It doesn't have too many answers, but the way you approach the problem, you may find one thing or another, and that becomes a challenge. So you have to make sure that, hey, it's fine to make this assumption, but then you have to double check, is everything fine? Are the two vehicles really moving forward? And you will find out if you do that, and please try to do it, because there's nothing like doing it, and then if you get a problem similar to it, then you solve it, and it's easy. So try to do it for this problem. Try to set up two equations with two unknowns, with the position of collision and the time to collision. The easiest way is to set up X sub c is the same coming from this car as coming from this car. And you set it up as a function of the t. Once you get the t, then you can figure out using an expression similar to what I did here, at what speed the two vehicles collided, right? So in this case, you will know the initial speeds in both cases, you will know the acceleration, you will have figured out the times, and you will be able to figure out the final speeds. If you get to that point and that's negative, then you say, okay, my assumption was incorrect. I could have started the problem like this. You can do either, right? Either is fine. The question is that you have to make sure that your assumption is correct. Basically, the next slide, if you see here, is basically what we have been discussing. And in here, I tried to put, actually, I created this graph initially with Excel, and you can see this what happened in that problem if you assume that the two vehicles collide. What happens is that the intersection, you're going to find it when intersection of the two lines when this vehicle is already going backwards. And in that case, what you have to do is to say, no, this vehicle stopped, and I want to find that time and the speed at which that happens. So basically, this slide tells you what we have been discussing. I added these two slides beyond what we covered in class to give you some better idea of the type of problems that you may face that are some variations of the problem we discussed in class at length. In this situation, this is similar to the situation in one of the problems in the problem session. We have two vehicles, vehicle 1 and vehicle 2, traveling in opposite directions. Like I mentioned in class, this will typically be the situation when you see vehicles traveling on vertical curves or in some winding horizontal alignment where they do not see each other up to some point in which they do, and then they need to take some action. And in this case, we're assuming that the only action is that they can brake. So vehicle 1 is traveling at an initial speed v1 node, vehicle 2 at an initial speed v2 node. I will typically give you some information about the frictional forces they can use or the acceptable deceleration rate. In addition to that, you will have some information about the grade of the road, and with that you can compute, as we saw also in some of the problems, that if you have a constant grade and a constant friction coefficient, that generates a constant deceleration rate if we assume that we can neglect air resistance and rolling resistance. So in any case, we will have some initial speed for each vehicle and a deceleration rate for each vehicle. With that information and with the perception reaction time of the driver of each car, we can figure out whether these two vehicles will collide or not. So what we see in this figure is that vehicle 1 will travel at constant speed during the perception reaction time of the driver of vehicle 1, and then it will start decelerating with constant acceleration rate, A1. And with that information, like we have seen before, we can figure out the distance needed to stop that vehicle from this time 0 up to a certain time t. So this is called delta x1 in this problem. And we can do exactly the same thing for vehicle 2. That will give me delta x2. So we have a perception reaction time that may be different for the driver of vehicle 2 and the driver of vehicle 1. We have the total distance traveled, and notice that with these equations, with equations of moment, what we can do is get the position of each vehicle as a function of time. The only difference in this problem with what we have done so far is that this position, like in the previous problems, is increasing over time, but the position of vehicle 2 as a function of time is decreasing because that vehicle is traveling in the opposite direction. And that's all there is to it, to this problem. Like I mentioned before, for real situations, you will have variable grades on vertical curves to make it simpler for the class. If I give you anything like this, it would typically be with a constant grade. It's not realistic, but to simplify the problems a little bit. And to answer the question that would typically be, would the vehicles collide or not, and if they collide, at what time and position? In this diagram, we can clearly see that if you compute a delta x1 and a delta x2 whose sum is greater than the initial separation d, then that tells you that these two vehicles collided at some point. And all we have to do is to make the position at the moment of collision for vehicle 1 and vehicle 2 to be the same. So for each of them, this blue line would be an equation, this red line would represent another equation as a function of time. We make those two equations equal to each other, the two positions are equal, and that would result in a function of time, typically a quadratic function, and you will be able to solve for that time of collision and the position at collision. On the other hand, if when you compute delta x1 and delta x2, you find out that their sum is less than d, that means that when the two vehicles are stopped, they would be separated at a distance s, and that typically would be one of the questions. Well, if they do not collide, what's the separation when the two vehicles were stopped? This problem is, again, very simple. It's similar to the assignment I gave you the other day, where you can figure out these two distances, and with that tells you whether they collide or not, so you don't have to make many assumptions. You just compute those two distances. That will tell you have either this situation or that situation. And if you have this situation, it's a little bit more complex, but relatively easy to solve. Another situation occurs when we have vehicles entering from a non-ramp to a freeway. So this would be represented here by this red vehicle trying to enter the freeway at a relatively low speed and trying to accelerate. So you see we have here a parabola representing a constant accelerated movement of a vehicle entering the freeway. And again, constant accelerated movement to make it simple for this class. Now, if that vehicle enters and doesn't look at the vehicles that come on the right lane on the freeway, he or she may cause a dangerous situation. So the driver of this blue vehicle, after a certain perception reaction time, noticing a danger, will have to make a decision whether to slow down. Again, I may give you the grade of the road and the coefficient of friction, and with that you may have to get the deceleration rate, or I may give you the deceleration rate directly. In any case, the situation would be that after slowing down, and this is a common situation every day when you drive, after slowing down, the two vehicles reach a certain minimum distance, but then that distance starts increasing because this person continues accelerating, or at some point may decide to continue moving, and this vehicle continues accelerating. But this is a situation we're interested in. What would be the minimum separation between the two vehicles and at what time they occur if they do not collide, or whether this happens when this vehicle enters recklessly the freeway, the vehicle behind may not have enough time to decelerate and hits the vehicle in front from the back. In this situation, like before, we would be interested in the time of collision and the position at which the two vehicles collide. Unlike the two previous scenarios I discussed before, where we were able to compute the distances needed to stop each vehicle, and with that we were able to say whether the vehicles collided or not, here you don't have that luxury. The situation is either that you get some minimum separation or they do collide, and you need to find out which of these two scenarios are true. So if you start a problem like this, basically you can assume, you can compute for this type of problem to get the minimum separation. You can very easily set up one equation, or two in this case, that gives you the separation as a function of time. It's very easy for you to compute this position as a function of time. We're assuming constant acceleration. Then this is a quadratic function that you can compute very easily. And for the follower vehicle, for the vehicle behind, during this period of time, TP1, during this period of time, he's moving with constant speed. So this is a linear function, very easy to determine. And then after that, it starts accelerating. This is a quadratic function. The point I'm trying to make is that this separation, which is also a function of time, you take this position minus that position, or this position minus that position. These two are functions of time, and therefore the difference is a function of time. So it's a very easy function to compute. Now, that function is one thing during this interval, TP1, and it's a different thing After that, now you have this quadratic function subtracting this other quadratic function. So the difference between two quadratic functions, it would be another quadratic function. So we don't know whether the minimum occurs after TP1 or before TP1. Typically it would be after, but it depends on the data. So don't assume that's the situation. So basically you set up those two functions and you choose one or the other. You start with one, and let's say I would typically start with this. After TP1, I would have this quadratic minus that quadratic. That would give me the separation as a function of time. And in order to get the minimum, you do what you did in calculus. You take the derivative of that function with respect to time, set it to 0. That will give you a critical point, which is the location of a minimum, a maximum, or a point of inflection. In this case, we will find the minimum. We will find the time at which that minimum occurs. And then when we plug back that time into the function giving me the separation as a function of time, we will get the minimum value. Some things you need to be careful is that when you find this minimum, this time at which the minimum occurs, if you find that this value is less than TP1, that tells you that the minimum did not occur in the area for which your function was valid, and therefore you have to analyze the function giving you the separation over this range from 0 to TP1. That means that the minimum may be occurring there. The same thing, if you started the problem here and you get that the time at which the minimum occurs according to this function happens over here, that tells you that it did not really happen over here. That tells you have to use the other function. So that's one of the things you have to be careful with. The other thing you need to be careful is that when you find the time at which the minimum occurs, you may, when you plug that value into the separation as a function of time, you may find that that value is negative. What that is indicating is that what you have really solved is a problem similar to what you see here, where the two lines intersect, and they intersect at more than one point. And what that tells you is that over here, that separation is negative, meaning the vehicle that was behind is now in front. And that basically tells you that the vehicles collided. So the assumption, the way you started the problem was not the right assumption, and therefore you have to now go back here and make this equation equal to this equation and solve for TC and X sub C in the same way we did in the previous problems. By the way, this also illustrates why you typically get two roots for the time for collision and why you have to use the minimum of the two. And with this, I hope I am giving you a much better idea of all the variations you may have and where the pitfalls sometimes are. Like I mentioned before, solving these problems graphically helps a lot, and it's a very valid way to do it. But I also want to instill in you the ability to solve things analytically, because if some of you want to go for research or to do research or to develop some equations for some particular problem, you need to develop some of these skills.